Hello everyone. In this video we are going to discuss some of the basic properties of scalar product or dot product of two vectors. We have already discussed in the previous video that if two vectors are there given by vector A dot vector B, so it can be written as AB cos theta, or in terms of the components of I cap, j cap and k cap, vector A dot vector B can be written as AX BX plus AY BY plus AZ BZ. So let us see how we can represent different properties of scalar product of two vectors. The first property that we are going to discuss here is the scalar product is commutative in nature. By commutative in nature, we mean that vector A dot B is equal to vector B dot vector A. Okay? So that is the meaning of commutative. So let us prove it also. See, we know that vector A dot vector B is given by AB cos theta, where theta is the angle between vector A and vector B, right? Now always remember, the angle theta is measured in the anti-clockwise direction. Suppose we take this figure. In this figure you can see vector A dot vector B. So this angle is taken in the anti-clockwise direction from vector A to vector B. Okay. Now when we will measure vector B dot vector A, we have to again take the angle between them in the anti-clockwise direction, that is from B to A, and that angle will be 360 minus theta. Okay. So if this is the case, then vector B dot A we will be writing as BA cos the angle between B and A when traversed in the anti-clockwise direction will be given by 360 minus theta. So we write BA cos 360 minus theta, and the value of cos 360 minus theta is cos theta. So it is BA cos theta, and then it can be written as AB cos theta. So what we can see here, that B dot A can be written as AB cos theta, and AB cos theta is A dot B. So we can say that vector A dot vector B is equal to vector B dot vector A. I hope this is clear to you. See here, the angle between vector B and vector B and vector A is taken in the anti-clockwise direction. So therefore we can write that the scalar product of two vectors is commutative. That is, A dot B will be equal to B dot A. Okay, now the next property is the scalar product is distributed over addition. That means vector A dot vector B plus vector C can be written as vector A dot vector B plus vector A dot vector C. So let us see, we are going to prove this. Let us see how it can be proved. Three vectors we are going to consider first. OR represents vector A. This represents vector B, and here it is vector C. Now the component of vector B along vector A, we drop a perpendicular here, so OP represents the component of vector B along vector A. Similarly, the component of vector C along vector A will be PQ. Here we have to drop two perpendiculars, so PQ represents the component of vector C along vector A. Now we can see here, using the triangle law of vector addition, we can write vector B plus vector C, and this is the resultant which is written as vector B plus vector C. So in the triangle law we know that the two arms of the triangle are taken in the same order as vector B and vector C. So the resultant is given by vector b plus c. And the component of vector b plus c along the vector A is OQ. So these are the components, these are the vectors which we have considered. Now let us prove the distributive nature of scalar product. See, we have to find the scalar product of vector A dot vector B plus C. So we know that the dot product of two vectors is given by the magnitude of the first vector, that is magnitude of vector A, into the magnitude of second vector along the first vector, that is magnitude of the component of B plus C in the direction of A. So magnitude of A, from this diagram we can see the magnitude of A is OR, and the magnitude of B plus C, component of B plus C along vector A is OQ. Okay, so what we can write is magnitude of vector A, which is OR, into magnitude of the component of vector B plus C in the direction of A, which is OQ. So here we can write OR into OQ. I hope this is clear to you. So if this is clear to you, then we can write here OR into OQ. OR into OQ, this is the value of vector A dot B plus C. So OQ is written as OP plus PQ. We can see here in the diagram, OQ can be written as OP plus PQ. Now here these are the magnitudes only, OR, OP and PQ. So we can use the distributive property. We can write here OR into OP plus OR into PQ. Okay. Now the values of OR is the magnitude of vector A, and OP is the component of vector B along vector A. That is, we can write here B cos theta. So the first term here is magnitude of A into B cos theta, that is AB cos theta, which can be written as A dot B. That is OR into OP can be written as A dot B, plus OR into PQ. PQ is the component of the vector C along vector A. So what we can write is OR is the magnitude of vector A into magnitude of vector C in the direction of A, that is C cos theta. So we can write here as vector A dot vector C, that is OR into PQ can be written as vector A dot vector C. So we have the result here for vector A dot vector B plus vector C will be equal to vector A dot vector B plus vector A dot vector C. So we are going to see the same thing here, vector A dot vector B plus vector A dot vector C. Okay. So here we can say that the scalar product is distributive over addition. I hope this part is clear. Now let us move to the third property, where the two vectors, vector A and vector B, are perpendicular to each other. Now always remember, whenever the two vectors are perpendicular to each other, that is the angle between them is 90 degree, then when we solve for dot product A dot B, vector A dot vector B, which is AB cos 90, and cos 90 is 0. So always remember, whenever two vectors are making an angle of 90 degree with each other, their dot product is always 0. Now if vector A and vector B are parallel vectors having same directions, naturally the angle between them is 0 degree. So vector A dot vector B will be AB cos 0, and AB cos 0 is 1, so it is AB. That means the scalar product has the maximum positive magnitude, and this is the maximum vector A dot vector B. This is the maximum positive magnitude, which is AB. Okay. So the next fifth property. Here you see, if you consider vector B and vector B are two parallel but in the opposite direction. We can call it anti-parallel. That means the angle between them will be 180 degree. Then the scalar product is the maximum negative magnitude. That is, vector A dot vector B will be written as AB cos 180, and cos 180 is minus 1. So it is minus or the negative of AB. So this is the maximum negative value that we can have for the dot product of two vectors. Earlier we have seen that when it is 0 degree, the angle is 0 degree, then we can have the maximum positive value, which is given by AB. I hope this is clear to you. Now we'll move to the next property here. The next property is if the dot product of the vector with the vector itself is taken. Like suppose you take vector A dot vector A. Now we know the formula, product of the magnitude of the two vectors into the cos of the angle between them. So it is A into cos 0. 0 because both the vectors are in the same direction. So we write here as A square. That is the square of the magnitude. It can be written as in the form of modulus sign, vector A modulus, that is only the magnitude only, and we are taking the square. So scalar product of a vector with itself is equal to the square of its magnitude. Okay. Now let us see the seventh property. The scalar product of two similar base vector. Base vector is actually the unit vector. You must be knowing there are three unit vectors in three directions. Along x-axis it is I cap, along y-axis it is j cap, and along z-axis it is k cap. So scalar product of two similar base vector is unity, that is 1, and that of two different base vectors is 0. Let us prove this. Like I dot I, that is I cap dot I cap. These are the two unit vectors or the base vectors which are similar. So their magnitudes are multiplied 1 into 1, and the angle between them is 0 degree. So it is 1 square, which is 1 only. So if the vectors are similar, I dot I, similarly j dot j and k dot k, all will have the same value 1. But when the unit vectors have different values, like suppose we consider I dot j, in that case it will be 1 into 1 into cos 90 degree, because the angle between I cap and j cap, x-axis and y-axis is 90 degree. So it is 0. So whenever two different unit vectors are there, like I cap dot j cap dot k cap dot I cap, all the values will be 0. So you have to always remember this. Similar vectors, their dot product is 1. If the vectors are different, unit vectors are different, then their dot product is 0. I hope this is very clear. We move to the next property. The scalar product of two vectors, that is vector A and vector B, is equal to the sum of the product of their corresponding rectangular components. This you need to understand. If vector A is represented by AX I cap, AY plus AY j cap plus AZ k cap, and vector B is represented by BX I cap plus BY j cap plus BZ k cap, then vector A dot vector B will be given by the product of the components of I cap plus the product of the components of j cap plus the product of the components of k cap, that is AX BX plus AY BY plus AZ BZ. So I hope this is also very clear. And the last property that we are going to discuss here is, we know that vector A dot vector B is given by AB cos theta. So obviously the value of cos theta will be vector A dot vector B divided by AB. A and B here are the magnitudes of vector A and vector B. Like it is written in terms of modulus, you can simply write here AB. Now vector A dot vector B, we have the value we have already considered here. It is AX BX plus AY BY plus AZ BZ. And the magnitude of vector A is root over AX square plus AY square plus AZ square. Similarly for vector B, the magnitude is root over BX square plus BY square plus BZ square. So this is the way in which we can represent cos theta. And we can actually calculate the value of theta. So I hope this is very clear to you. Any doubt you can